All right, so we're gonna do example number 1 here. And a lot of times with these examples, they'll use a wrench because you can figure out how much force you're applying on a wrench and how long the wrench is, and it makes it pretty nice. Or they'll use like a door. And this is what I've drawn here. It's the top view of a door. So here's like the top of the door, and here's the hinge right there. So when they put a hinge on there, that's really obvious that that's gonna be your point of rotation. So everything's gonna be referenced relative to that point of rotation right there. Sometimes when the object's not moving, it becomes a little tougher, and we'll talk about that in our later examples. But okay, so example 1, you have the top view of a door, and we've probably all done this before. If you were going to open a door, do you want to press really close to the hinge, or do you want to press way out here on the edge where the handle is? You want to press out here, right? We've all accidentally pushed right here before, and it doesn't really cause the door to rotate open very well because your R value is so small that you'd have to apply a great force to get that door to rotate. So if you want to maximize torque, we're going to apply 100, what I have here for our given to say. All right, you're going to apply a force of 100 newtons, switch colors. And let's say this door is 2 meters long, like over 6 feet long. Just make up some nice numbers. And that 2 meters is relative to your point of rotation. So 2 meters, you're going to apply a force of 100 newtons. In the top view, we're going to say, hey, we're just going to press, boom, right at the edge of the door here with 100 newtons of force. That'll actually be pretty interesting because you're maximizing your torque because you're putting your force at the maximum lever arm. So when you want to figure out your torque, you're going to say, okay, and for the symbol for torque, they use the Greek letter tau. It's kind of got a cool looking T right there. Yeah, it's kind of fun to draw. So it's your force times your radius, your lever arm. They call it your lever arm because it's relative to your point of rotation right there. This is like the length times the sine of the angle between your force vector and your R right there. So in this case, the force they told you you're applying with, they're saying, hey, you applied 100 newtons. They said you applied that 100 newtons 2 meters away from your point of rotation. That's like your 0 point. Your point of rotation is like your 0 point. You're 2 meters away from that. Times by the sine of the angle. In this case, it's the sine of 90. Because picture this. Your force vector is pushing that way. Your lever arm vector, your R, is going to the right. So the angle they make there, that one's going up, that one's going up. That's 90 degrees between your R and your force. So the sine of 90 is going to be 1. And that just means you have maximum torque, right? Because if you're going to try to open this door, it makes the most sense to push 90 degrees relative to the lever arm right there. So you do this, that's 1, 2 times that. That'd be 200 Newton meters of torque. Now, one thing, it's really important. We got to talk about how they define a positive torque. If you picture you apply this force and it's going to cause this door to kind of open in a counterclockwise fashion. So that's what they call a positive torque, 200 Newton meters. Or you could write it as 200 Newton meters counterclockwise, CCW. It's a lot like the unit circle. Remember the unit circle opens up counterclockwise positive. They define counterclockwise torque, so that way, as a positive torque, and they define clockwise torques as negative torques. So just make sure you can either say 200 Newton meters positive, or you can say 200 Newton meters counterclockwise. If you're ever in doubt, I like to put counterclockwise, just 200 Newton meters counterclockwise, because that's really obvious that it's going that way. All right, so that's part A. Let's look at part B. Same setup here, but now instead of pushing at 90 degrees, you're going to push at 30 degrees. So I'm actually just going to do a real quick little sketch of what that look like. It's a horrible door. We'll go with it. And you're still going to push at the end. You're still going to push the end, and you're going to push with what? How it was 100 newtons of force? Perfect. 100 newtons of force. And here's the thing. When you push at an angle, you know right now, if you want to maximize torque, you want to cause that door to open, you want to push at a 90-degree angle relative to it because you're going to maximize that torque because the sine of 90 is 1. Well, if you push at an angle of 30 degrees, when they give you that angle, that's relative from the force vector to your lever. This is your lever arm right here, the R. This is your force vector, and this would be 30 degrees right there. Okay, so when you do that, when you work the formula right here, we're going to say, okay, I find out how much torque this is. It's going to be 100 newtons. Still, you're pushing it 2 meters away from the hinge times the sine of 30 degrees. And the sine of 30 degrees, just to check, I believe that's 1/2. So 1/2 times 2 times 100, and your torque's going to drop to 100 Newton meters. So it's still going to be positive, 100 Newton meters, or you could say 100 Newton meters counterclockwise, but your torque got cut in half. And you might be like, well, why am I having less torque? Why am I causing this door? It's going to rotate, still going to rotate open, but you're going to have a lot less torque. You're going to have half as much torque. Well, let's take a look at this right here. When you push at an angle, let's zoom in here. When you push at an angle right here, 100 newtons, it's got a vector that's going up, and it's got a vector that's going over. And you have, let's just say in this angle right here is 30 degrees. So when you look at this, this orange vector, that's what causes the door to open. So if you want the door to open, you want to maximize the perpendicular component of this vector right here. So in this case right here, when you just push straight up perpendicular at it, you maximized it, right? Because the sine of 90 is 1. Well, right here, when you push with the hypotenuse at 100 and the sine of 30 degrees times 100, you're only going to pick out this part right here. So you can see you're going to have less torque because some of your vectors are going to be hung up in this red component right here, like the x component of the vector. So when you're pushing an angle, you have an up and an over component. This red component does not help you open the door. That does not contribute to torque. Okay, so it's only the orange part. That's why you're saying, oh, of the 100 newtons, I only get to pick out the sine component, this orange part right here. That's what's contributing to the door opening. So that's why when you say, oh, 100 sine, you're only 50 of those newtons are really going toward opening the door, right? 50 times 2 gets you the 100 newton meters of torque. So it's really important if you want to maximize torque, you want the angle between the R and the F to be 90 degrees. Anything less than that, it's going to be less than maximum torque. So that's just kind of a recap of how to calculate torque, and it's very simple. So they can just straight up say, hey, find your net torque, and they'll say the net torque because you just add them up. You can have multiple forces acting on the same door. Maybe you have some person pushing from that side trying to stop you from opening the door. I don't know why you'd want to do that, but so that's the simple examples. Make sure that makes sense before you rock on to example 2. Example 2, this is going to be one of those doors where it's a revolving door where you have the hinge right in the middle. This lever arm is 2 meters to this point right here. This lever arm is 2 meters to that point here, so I kind of made it nice and symmetric there. And we're going to have force 1 pushing 20 newtons at 90 degrees, and force 2 is going to be pushing 40 newtons at 90 degrees. And they just want to find the net torque. So this is the top view again. Top view. And I haven't drawn my force vectors on there, and that's really going to make a difference how I draw them. I'm going to try to think how I want to do this. Yeah, let's do it like this. Let's say one person's right here at the very edge of the door and they're pushing it with their 20 newtons. 20 newtons, right, like that. And technically that's 20 newtons, and this one's gonna be pushing at 40 newtons. I should make that one twice as long. And let's say somebody over here is trying to push on this revolving door with 40 newtons. And even before you do any fancy physics calculations, you'd say, who wins, the person pushing at 40 newtons at 2 meters, the person pushing at 20 newtons at 2 meters? Well, you know this person's going to win, so you know this overall system should be rotating clockwise. And remember, clockwise would be a negative overall torque, right? Because remember, unit circle, positive is counterclockwise, clockwise would be negative. But we're going to figure out the net torque. And so we're just going to sum up, just like we used to sum up forces, we're going to say, hey, let's sum up the torques. Totally legal. Sum up the torques. So we're going to sum up the 2 contributions of torque. And here's the deal. When you do this, step 1, you draw a picture. Step 2, you label the forces. Step 3, you're going to use your coordinate system. So that's the old stuff, coordinate system of forces. But one thing that's unique to torque, you have to address the point, and put a little star, point of rotation. So it's still the same good 5 steps for success that you're used to. Draw a picture, label your forces, make sure you have your coordinate system on there, x, y, things like that. But the new step you have to do at torque, because things are rotating, you have to identify the point of rotation. Step 4, you're going to sum forces if needed. In this case, they're not asking us to sum forces, so we're going to sum torques. It's a summation step, sum torques. You'll know if you need to sum forces, that's what we're going to do next. But I'm putting the old stuff's in purple. Draw a picture, label your forces, pick your coordinate system, sum your forces. There's just 2 little caveats here. You have to mark your point of rotation. So you put a little asterisk right next to where the point of rotation is, right there. And then you're going to sum your torques. And then the final step, solve. One time I made the joke, I put a little accent right there. I said solve, and then somebody got confused. So step 5 is solve. So in this case right here, we drew a picture, we labeled our forces, we picked our coordinate system, I put it right there. We're not going to use x and y forces in this because it's not that complicated of an example. You'll see on our next example we'll have to do that. But we did have to identify our point of rotation because that's kind of where your 0 point is. That's what we're saying, hey, that's your 0 point. We're going to reference things relative to that. You're going to sum your forces. Once again, we're not really going to talk about forces in this one because it's a more simple one. So we're going to sum our torques right now, and then we're going to solve. Okay, so let's sum our torques about this point. We sum torques about a point of rotation. So in this case, this 20 Newton force, we'll write down 20 Newtons. So that's the F times the lever arm, in this case is 2 meters. And picture this, the angle right here of this one, this person's pushing that way, the lever arm's that way, and they're saying they're pushing at 90 degrees, so times the sine of 90. They have maximum torque because all of the force is going toward causing that door to rotate. And now we have to ask ourselves this. This force is going to try to make this door go counterclockwise. And that right there would be a positive torque because it's counterclockwise. All right? So that contribution, that is a positive torque. This dude over here, let's look at this person's torque. So we once again have a force, 40 newtons. 40 newtons times the lever arm, which is 2 meters. And this force as well, you know, they could mess around with the angle and make it like 30, and it's always the angle relative between the R and the force right there. But once again, they just made a nice 90 degree. He's pushing up. This one's pushing up. This one, the lever arm's right there. So sine of 90. Just like that. But now here's the thing. This force is trying to make this rotate clockwise. So it's really important. We're going to assign that a negative torque contribution. So this one's the purple one's trying to cause it to rotate counterclockwise, which is positive. This one's trying to do the opposite thing. It's making it try to go clockwise, which is negative. And we're just going to sum up our torques to get an overall net torque. And you might be thinking, hey, we used to sum forces set it equal to MA. We can sum torques and set it equal to M's become I's and A's become alphas, but don't worry about that today. So what is that? Sine, that's what? That's 40 Newton meters. 40 Newton meters minus 2 times 40, that's 80 Newton meters. Sine 90 is 1. So your net torque is going to be negative 40 Newton meters. That's your net torque. You can either write it the sum of the torques equals that, or net torque. It's just saying the same thing. And that negative says who wins? Well, the red one wins, and it's going to cause a net torque of negative 40 Newton meters. Or you could say 40 Newton meters clockwise. You could say that. Clockwise. Just like that. So that was just us summing our torques for a nice, revolving door, top view situation of a revolving door there. The big thing you want to write down, these are your 5 steps for success. And they're all the good ones you know. It's just that we have like 2 little torque things we add on there. You have to find your point of rotation for torque, and you also have to sum your torques. We didn't sum our force in this one. We're going to do that next. So that'll be a more complicated example. We didn't need to involve that for this more simple example. So make sure this makes sense before you watch the next video. All right, thanks for watching.